start with observability of the system in a state space. Now, what is meant by observability? Last time we have seen the controllability of the system. The controllability means concerned with that there are some states which are at initial time and it has been transferred at time t equals to tf, and we are all the states we can found all the states. That means that the system is controllable, but all the state which has been reached, really they are observed or not, that is also very important, because sometimes it may possible that all the states which are present that has been reached or that has been transferred, but they can't be observed, and if the states can't be observed, it means that system is not observable, and that is also create a problem, particularly in controller design. Now, first of all we see what is meant by observability of the system. Observability, so every state x of t0 can be completely identified by measurement of output yt over a finite time interval. So, here this part is concerned with the output, because if you see the state space model, x dot equal to ax plus bu, y equal to cx. So, now the output is also related to the state, this output y is also related to state x. Therefore, every state can be completely identified by measurement of output yt over a finite time interval. System is observable if every state can be determined from the observation of y of t over a finite time interval. Every state affects the every element of the output vector. That means, so all these points indicate that there exists a relationship between the state and output. Now, we will see through this concept through general example. So, in last two parts, means particularly in state controllability, observability, I have explained you the one example. Now, here as I told earlier, as my industry trip is going from Roorkee to Delhi. So, there are say x10, these are 10 students, there are 10 students, they are at IIT Roorkee and they are going to Delhi, and now x1, x2, x10. Now, here they are 10 state, and whatever output is required, here is y, and let us say this is also a y of t naught and say y of tf, this final time. Assume that we are considering a teacher is particular output, the teacher is concerned with these states. So, y output is a teacher where there is involvement of 10 states, and here at y equals to tf is also there is involvement of 10 states. Now, what happened? All 10 students are there. Now, all 10 students has been reached here. Now, here we found that all students has been reached, that means the system is your controllable, but concerned with the output. Why? Output here I am talking about the teacher. When teacher start counting the 10 students 1, 2, 10, that particular student is, let us say it is inside that particular bus. I mean I am counting the students, but it is found that even though student present in the bus, I can't identify him. That means, in the output, instead of 10 students which has been there in the bus at Delhi, I am identifying only 9, but the 10th student is reached there, but I can't identify it. That means that this system is not observable, and there also when I am not observing that particular student, then definitely it is tough for me to take decision whether to go to industry or to go back to Roorkee. It means that whatever states are there, they are at initial time, they have to reach at final time. Along with that, that means that controllable, when they reach here, that means they are controllable, and when we counted it, that must be observable. Therefore, controllability and observability both are the same thing. Now, we will see how they are useful in a controller design. This control design part will come later on, but now as this issue is related to our controller design, I would like to discuss few points. In a state space analysis, the controller is designed based on the state information, whereas in classical control the controller has been designed based on output and input, but in a state space the working of controller is based on the states as well as the input output both. But you see that in the output y is concerned with the state if any of the state is not observed, or if sometimes it is not possible to measure that state, then what is the option for available for me? I have to identify the state. Sometimes you have seen that we are going for some doctor for some treatment, and sometimes doctors say that you do the test, but because of time limitations or non-availability we are not doing the test. Then doctor just putting some hands here, somewhere here near to heart, he will identify that particular states. That means that, so if that particular parameter, if it is not identified, then he can't prescribe the medicine. That means that state which can't be measured, that need to be identified. So if we identify this particular state, then we can say that control design is possible. But if the states is there but we can't identify it, then we can say that system is not observable, and therefore there is no need to it is not possible to design a controller. Similarly here, as I told you that all 10 states output, I am talking about the teacher, all students have reached, output is teacher. When students have reached here, although they are reached, but we can't identify, or teacher can't identify that particular single student, that is out of the 10 he identified only 9 students. Therefore this system can't be observable. Now the next thing, mathematically how to check the observability of the system. And observable is there, and observability means is concerned with the output. Therefore the important role of C is here. We have seen that in case of state controllability, the state controllability QC, there is a involvement of only B, AB, A raised to n minus 1 B. There is no C is involved in the concept of controllability, but now when talking about the observability, you see that system is represented by this one, is completely observable if and only the rank of the combined matrix C transpose A transpose C transpose A transpose raised to n minus 1 C transpose, this is n. And here we will find that there is no involvement of B matrix. They are all related to A and C matrix. A is the system matrix, C is the output matrix, and they are all concerned with these states. Now how this equation has come? We have already seen the origination of this equation B A B A raised to n minus 1 P, and this we have determined, or this equation we have got from the state equations. Similarly here also, from the state equation itself we can get this particular equation. Now we start deriving the result C transpose A transpose C transpose A transpose n minus 1 C transpose. Definitely when we start any system, our model is same, x dot equal to Ax plus Bu, y equal to Cx plus Du. This is our state space model, and now here we are concerned with the observability, that means when we derive any equation, the output must come into existence. In case of controllability of the system, we are talking about only x of t, but here we are concerned with the output y of t also. So, y is depend upon x, therefore, we write first of all the equation of for x of t. This x of t equal to e raised to a t x 0 0 to t e raised to a t minus tau b u tau d tau. Now, this is state equation we have written. This is x of t, but now our final time is say t equal to Tf. Now, this equation we have to write in terms of final time Tf. Now, we can write this as x Tf e raised to a Tf x of 0 plus 0 to Tf e a raised to tau f minus tau b u tau d tau. Now, see every equation we have written, that means t has been replaced by Tf everywhere. Now, this is equation for x Tf, but we are concerned with the output. Therefore, output y with respect to time Tf is in as C matrix x of Tf plus d into u. Now, we replace this x of Tf in this particular equation. So, we will get C E A Tf x 0 plus C 0 to Tf E A Tf minus tau b u tau d tau plus d into u. So, in this particular equation we will find that all these parameters c, b, d, u all are known, and here also the same thing. Now, this complete equation we can write down, because these are known, in terms of directly x dot equal to ax and y equals to cx. Now, what we have done, because this c, b, d represent, if you move on the left hand side we get a output, and that output will get in terms of c, that is cx. Therefore, here final equation we have written x dot equals to ax, y equals to cx. Now, here from these equations we can write down x of t equal to E A Tf x of 0, and here y of Tf C x of Tf, we can write down this as C E A Tf x of 0, that is y of Tf equal to C e raised to a into Tf into x naught. Now, up to now we have reached now about this part e raised to a Tf. In case of controllability of the system, that is when we have derived the controllability equations, we have written this equation, that is equation means we have written e raised to a tau f Tf e raised to a Tf in terms of Cayley-Hamilton theorem. So, now this equation, that is equation means this e raised to a Tf can be written as alpha 0 t into a raised to 0 plus alpha 1 t a raised to 1 plus alpha 2 t a square. Therefore, E a raised to t f can be written as k equal to 0 to n minus 1 alpha k t into a raised to k. Now, we replace this equation in these particular equations. So, we can get y of t f, we will get y of t f, that is k equal to 0 to n minus 1 alpha k t to c a raised to k x naught. Therefore, y of t f, now we simplify this. So, we can get alpha 0 t c x naught plus alpha 1 t c a x naught, and this up till alpha n minus 1 of t c a raised to n minus 1 x of 0. Now, here alpha 0 t c x 0. Now, here alpha 1 of t to c into x naught alpha n minus 1 t c a raised to n minus 1 x 0, and here y of t f, you can take x 0 common. So, here x 0 x of 0 alpha 0 into final time t f. Now, this t, because we are talking final time. So, now t we have replaced here as a t f c plus alpha 1 t f to c into a, this basically c into a plus alpha n minus 1 c a raised to n minus 1. Now, this is the equations, this is the final equations. That means, y of t f we have got in terms of x 0 alpha 0 t f c alpha 1 t f c a alpha n minus 1 t f c a. That in this case we will find that c a and c raised to n minus 1, this plays a very important role. That means, particularly if you calculate the rank of this matrix, particularly c a raised to n minus 1, that should be full, that should not be 0 or that should not be false, because if it is false, this y of t f cannot exist. Therefore, we have to determine the rank of matrix of c a raised to n minus 1, and this must be n. The rank of this matrix c a raised to n minus 1 must be n. That means, whatever our statement Q observer matrix C transpose A transpose C transpose A transpose raised to n minus 1 T times, that has been proved. And this we have proved from these equations, that is C raised to n minus 1, because if this is part, if it is not observable, or if the rank fall in this particular case, that means any of the state has been shielded from this observations, and therefore, it is difficult in terms of a controller design, because all the states are very important, because they are sometimes they are somewhat interrelated. So, if you control one state, if one state cannot be controlled, it also affects our results. Therefore, all states must be observed, that is the mandatory for the controller design. Now, we see example. So, we have taken simple system. So, let us say A matrix as 0 1 minus 2 minus 3, and say B matrix as 0 1, and our C matrix is like this, C equal to 1 1, and this plant is nothing but x dot equal to Ax plus Bu and y equal to Cx. Now, our main purpose is to check the observability of the system. We have checked controllability as well as up to controllability of such type of example. Now, here point is that we have to check the observability of the system, and now the observability we are checking by Kalman test, and we have already seen the test. If you want to check the observability, we have to carry out the, or we have to determine the determinant of this particular matrix. If determinant is 0, it means that rank false, that is C transpose A transpose C transpose. Now, here now we are talking about this particular example, and now for simplicity we can write the observability matrix as Q observable as C CA, or we can write this as C transpose A transpose C transpose, that is here C transpose A transpose C transpose. So, here we can write down the matrix C. C is here 1 1, this one. Now, we want to determine here C into A. So, C is 1 1 and A matrix is 0 1 minus 2 minus 3. See, this is A matrix we have written here. Now, we have to solve it. So, this multiplied by this and this particular row multiplied by these columns. So, after multiplication of this, we will get this as minus 2 and this as also a minus 2. So, for checking the observability, we have got C, we have also got CA, and therefore, we can write observability matrix as 1 1, this 1 1, and here this minus 2 we can write down like this, and now we determine the determinant of this matrix, right, minus 2 this is 0. So, from this example we find that the determinant of this observability matrix is 0, that means rank fall, that in other words we can say that this particular system is not observable. So, we have seen that in this particular test, the problem which we have found that we are not getting the insight of the concept of observability. What we want, that we have to see that out of this which state is responsible for making the system unobservable, because that also helps us to go for some weaker notion, because sometimes in a practical sense nothing is perfect. Therefore, some approximation, some adjustment we are always making in the system. Therefore, this type of things cannot observed in such cases. Therefore, here we have to go for the Gilbert test of the observability. Now, how to solve the Gilbert test or how to perform the Gilbert test? We have already seen the Gilbert test, that is based on the concept of diagonalizations, and we have seen the diagonalizations, all states are separate. I mean, whatever thing is going on, each individual state we can easily observe. In other words, the states have been decoupled. Now, we see the what type of results we will get if you go for the Gilbert test of observability. So, now this concept is based on diagonalizations. So, I am taking a model as x dot equal to Ax plus Bu and y equal to Cx. So, x dot equals to Ax plus Bu, y equals to Cx, and now the concept of diagonalization is based on state transformation. You can take any of the state, you can assume any variable. So, for as we are assuming the variable k every times, earlier also, here also we are assuming assuming a new state in terms of k. So, here you can take x equals to mk. Now, k equal to m inverse x, and now this equation can be simplified as k dot m inverse x dot. Now, here m inverse x dot is equal to ax plus bu, and now this k dot equal to m inverse ax plus m inverse b into u. Now, this is m inverse a, this x is mk, and here is m inverse b into u. Now, k dot is like this. Now, this k dot equal to this m inverse am, we can write down as a bar k, and this is b bar into u. So, this is about the new state transformation in terms of k, but here is our problem is about observability, it concerns with the output. Therefore, although we derived, but this cannot solve our purpose. Therefore, we are concerned here is the output equations. So, output is our y equal to cx, and now here if you write y equal to cx, now here x is m into k, now here c bar into k. Now, we got y c bar into k, that means there is a involvement of say c1 bar, c2 bar, say cn bar into k. So, when we have seen the Gilbert test for controllability, we have talked about this particular equation a bar b bar, and we have seen that in a controllability, if any element of b bar is 0, then system is not controllable, that is concerned with the b bar. Now, here the observability test is concerned with the c bar, and c bar involves c1 bar, c2 bar, cn bar. Now, output y it depend upon k. Now, k is our new states, they are very important now, and if assuming that if the any of the elements in c1 bar to cn bar is 0, let us say if the c2 is bar 0, that means the k there is the involvement of various states say k1, k2 up to kn. So, this is c2 bar 0, that means the k2 state which is available for measurement earlier, because of this 0, this is not available for measurement, and therefore, we can say that the system is not observable in this particular case. That means directly we have got the information about the particular state which is not observable, whereas if you see the earlier examples, earlier methodology C, Ca a raised to n minus 1, here we have not got any information about the which state is observable or which state is unobservable, or whether all states are unobservable, no information, but whereas here we can get all information. Therefore, from practical point of view, from analysis point of view, I think we will definitely go for this Gilbert test. But as far as the numerical point of view, if for solving the examples or from academic point of view, we will go for the Kalman test. But both tests are important, and both tests are helpful in checking the controllability and observability. That is, in other words, we can say that is the first step of designing of the control, because whatever we are learning is final aim is to control design. If these tests are failed, it means that control design can't be possible. So, that in other words we can say that this Gilbert test as well as Kalman test is a necessary condition for the checking the controllability and observability, and now we are talking about the observability, that means it is also a necessary conditions for designing of the controller. Now, we see an example. Now, we will take the same system which we have taken earlier, say x dot as 0 1 minus 2 minus 3, this x say 0 1 u and y as 1 0 into x. Now, this is A matrix, this is B matrix and this is C matrix, A, B and C. Now, our aim is to check the observability of the system using Gilbert test, and Gilbert test is based on the model matrix. That means, we need to determine the eigenvectors. So, the first step in this case, we have to calculate the eigenvalues of this matrix. So, now lambda I minus A, so we will find that here this is lambda, this is minus 1, 2 lambda plus 3. So, if you solve it, we will get lambda square plus 3 lambda plus 2 equal to 0. So, if you solve it, we will get lambda 1 equals to minus 1, lambda 2 equals to minus 2. So, there are two eigenvalues, lambda 1 equals to minus 1, lambda 2 equals to minus 2, and this system is definitely a stable system. And now, we have to check the observability of this system. So, now the concept of diagonalization we are using, that means for each eigenvectors, for each eigenvalues we have to calculate the eigenvectors. And eigenvectors, there are two different processes we have already seen, and but we have seen that if you are given system matrix, it is a companion form, that is 0 1 minus 2 minus 3. So, if this is the arrangement, we will directly write the eigenvectors of a given eigenvalues. So, for this case, we can write down the model matrix MV, this M which you had taken earlier, this M, and what I am talking about MV, they are same, but V is the van der Monde matrix, because van der Monde has developed this one. That is why for this case we are writing down the model matrix as MV, this is also as called as M matrix. So, here write 1 this is the arrangement, and this is minus 1 and minus 2. We have already seen how to write in this, that is the general form of this, so 1 1 like this, lambda 1 square, lambda 1, lambda 2, lambda n, and here lambda 1 raised to n minus 1, lambda 2 raised to n minus 1, say lambda n raised to n minus 1, 1 1 1, lambda 1, lambda 2, lambda n, lambda 1 raised to n minus 1, lambda 2 raised to n minus 1, lambda n raised to n minus 1. So, here 1 1, and for this lambda 1, lambda 2 has been written as minus 1 and minus 2. So, M we have got directly. Now, we are talking about y equal to, if you see here, Cm into k. Now, here you write down this as C M V into k, that is here C bar into k. Now, we have to determine this, we have to determine here C into MV. So, C is here 1 0, and here our MV is 1 1 minus 1 minus 2, and here we can write down this as 1 multiplied by this. So, here we will get 1, and here you multiply it, we will get 1x, this is k. Now, here we have got, solving this one, we have got 1 1. So, CMV after solving this 1 0 1 1 minus 1 minus 2, we got 1 1, and now this y equal to 1 1, this is k, and this is nothing but your C bar into k, and this is nothing but 1 1 at 2 state, we can write down k 1 k 2. So, there are two states K1 and K2 that are transferred state. For each K1 K2 we have got this one and this one. That means these states are available for observations, and therefore we can say that by means of this concept our system is we can say observable system. Now, the another problem is that if there is a involvement of state space model, and state space model involve the multi input multi output system. That means if we have output y1, y2, ym, and there are involvement of say C11 bar, C12 bar, say C1n bar, then here C21 bar, C22 bar, C2n bar, Cn1 bar, Cn2 bar, Cnn bar, and here is say K1, K2, say up to Km. K1, K2, this is Km, this is Km. Now, this is complete y equal to C bar into K, and now C bar involved all these elements. It can be 1, 2, 3, say 4, 5, 6 and any of the elements. So, all the elements are involved. Now, in that case how to check the observability of the system, and this output y we have got from the concept of diagonalizations. The C bar we have got is. So, how to check the observability of the system? So, in that case if any of the column elements should be 0, if any of the column elements are 0, then we can say that the system is not observable. So, that is the case when we are talking about the multi input multi output system. That means, if any of the column elements are zeros, that is any columns any of this, then we can say that system is not observable, and most of the time we have a multi input multi output system, but particularly robotic arm systems, then we have process control system, a power system, everywhere multi input multi output system. Therefore, if you are talking about the practical point of view, we have to go through this multi input multi output plot, but as far as the sometimes the academic point of view, we are talking about the single input single output system, and the most important concept we have understood that if any of the element in the C matrix is 0, that means that that state is not available for the observation, and hence we can say that that particular system is not observable. Now, these are some references.